Hello guys, welcome back to the Foolish Engineer. To maximize efficiency and slash charging times of the EV, the industry is shifting to high voltage systems. With that comes high currents. And BMS depends on high accuracy current sensors like Shunt, Hall effect, and TMR sensors to measure those high currents and monitor battery health perfectly. Let's see how that happens. Do you know why are we engineers moving battery packs from 48 volts or 100 volts to 400 volts and 800 volts? Well, we aren't doing this for just to have a bigger number on the marketing brochure. We are doing it because of the Ohm's law and his minor cousin, the power equation. We know that the power is equal to voltage into current. If you want to charge a car at 350 kilowatts, because we have bigger batteries and which is enough power to run a small neighborhood and we stay at 400 volts. We have to push nearly 900 amps of current. To carry 900 amps perfectly or safely, we would need copper cables as thick as our arms. They'd be heavy, impossible to bend, and they'll get so hot they could cook a meal in seconds. But if we double that voltage to 800 volts, the math changes. To get the same 350 kilowatts, we only need half of the current, around 430 amperes. Because heat generation is tied to the square of the current, cutting the current in half reduces our heat losses by a massive 75%. So 800 volts lets us use thinner, lighter cables and charge much faster. But here is the catch. How on earth do we measure 500 amperes of current accurately when the voltage is high enough to jump through the air and fry our delicate 3.3 volt microcontrollers? Today, we are going to dive deeper into high voltage current sensing to see how we manage this beast. One of the key reasons I started this YouTube channel is to bridge the gap between the outdated Indian education system and actual skills needed in the industry. Well, if you're a student, you can use and learn an industry leading EDS software, Altium, for free by using its student lab program, which narrows down this gap. You just need to use your university email to enroll, and you get a full student license, a full PCB design course, and a certificate recognized by top Indian core electronics industries. Altium isn't just one PCB design software, but it is a whole platform of capabilities for electronics design. I've personally used Altium since the start of my electronics journey, and I honestly recommend it. It's a fantastic way to enhance your skills and increase your chance of landing a job in a core electronics company. So don't miss this golden opportunity. When we launch an EV at a stoplight, the current spikes from 0 to 1000 amperes in a heartbeat. When we use regenerative braking, the current flows backwards. Our BMS needs to track every single electron going in and out to calculate the state of charge. In an EV, if our current sensor is off just by 1% after a few hours of driving, the car might tell us we have 50 kilometers of range. But we are actually about to die on the side of the highway. This is called Coulomb counting. The stakes are massive, and that's where a current sensor comes into picture. We should select a current sensor that can measure a tiny 100 milliamperes when the car is sleeping and 1000 amperes when it's racing, keeping the 800 volts lightning side away from our sensitive brain low voltage side. And speed. If there is a short circuit, we need to detect it in microseconds to blow the fuses. So, what our options are? Let's break down the technologies. The shunt is basically a very precise piece of metal with a known ultra low resistance. It is placed directly at the path of the high voltage cable. As the current flows through it, it creates a tiny voltage drop, and we use Ohm's law to calculate the current. However, because we are physically touching the 800 volts line, we can't just plug this into a BMS. For that, we have to use an isolation amplifier to get the signal. Well, shunts generate heat. If you push high current through even a tiny resistance, that metal gets hot. Like very, very hot. Hot, hot, hot. What if we don't want to cut the cable to put a shunt in? What if we want to measure the current without actually touching the high voltage? Whenever electricity flows through a wire, it creates an invisible magnetic field around it. The more current, the stronger the field. We can feel this field using the Hall effect. Imagine a river. If we stand on the bank, we can feel the wind created by the rushing water, even if we don't touch the water. A Hall sensor works like that. When a magnetic field from our EV cable hits it, it pushes the electrons inside the sensor to one side, creating a tiny voltage drop or creating a tiny voltage. The best part, galvanic isolation is built in. There are two types of Hall effect current sensors. One is open loop Hall sensor and other is closed loop Hall effect sensor. The open loop Hall sensors are easy, but they have a big problem. They are drifty. If the temperature changes, the sensor's reading changes. If there is a magnet nearby or the car's motor is spinning, the sensor gets confused. It's just too noisy for a precision 800 volts BMS. To fix the drift of the open loop sensor, the engineers created closed loop Hall effect sensors. Imagine a tug of war. The big current in our 800 volt cable is like a giant pulling the rope to the left side of its magnetic field. Instead of just guessing how hard he pulls, we give the sensor a robotic arm. This robot arm is very smart. Every time it feels the giant pulling it left, it instantly pushes its own current into a tiny coil to pull the rope back to the right. Its only goal to keep that rope perfectly at the middle, at exactly 0. And to find the current flowing through the big cable, we just have to look how much work the robot arm had to do to keep the rope balanced. It's like active noise cancelling headphones for magnetism. It is super accurate, but it's also bigger and more expensive. Now, if we need more accuracy, like we need to know the current down to the last milliamp, then we move to the flux gate technology. Think of a flux gate sensor like a magnetic sponge. Inside the sensor, we have a ring of special magnetic material. We have a circuit that constantly pours magnetism into the sponge, flipping it back and forth from north to south, hundreds of times a second. When no current is flowing in our EV cable, the sponge fills up and empties at the exact same speed in both directions. But when we turn on our 800 volts battery, its magnetic field pre-fills the sponge. Now, when our internal circuit tries to fill the sponge, it saturates much faster in one direction than the other. By measuring the exact time difference between those two saturation points, we can calculate the current with incredible precision. Flux gate sensors have almost zero offset error. When the car is off, the sensor reads exactly 0. They are the gold standard for high-end EVs, but they are very, very complex and expensive. Now, let's talk about the absolute cutting edge, TMR, or tunnel magnetoresistance. This sounds like a science fiction because it uses quantum mechanics. Imagine a solid brick wall. If you throw a ball at it, it bounces back. It cannot go through. But in quantum world, if that wall is thin enough, let's say only a few atoms thick, the ball can sometimes just appear on the other side. That's called tunneling. A TMR sensor is made up of two magnetic layers separated by such ultra thin quantum wall. When our 800 volt cable's magnetic field gets near the sensor, it actually twists the magnetic alignment of these layers. When they are aligned, the quantum wall becomes paper thin and electrons tunnel through easily. When they are misaligned, the wall becomes thick and fewer electrons get through. TMR sensors are very sensitive. They are tiny, smaller than a fingernail, and they use almost no power. They give us the accuracy of a shunt with the isolation of a Hall sensor. Many engineers believe TMR is the future of EV current sensing. Well, if you want, we'll see about these complicated sensors one by one in detail in coming videos. So, as a hardware or BMS engineer, which one should we use? Let's look at our 4 contenders of a battle of the bests. First is the accuracy. If you are looking for the absolute king for DC precision, the shunt and flux gate are our champions. The shunt is superior with errors under 0.1%. The flux gate is right there too. It is excellent, also under 0.1%. The closed loop Hall sensor and TMR sensors are still very good, hanging around 0.5% range, which is plenty for most of everyday driving. Second is isolation. This is where the magnetic sensors win easily. Hall sensor, flux gate, and the TMR all have inherent isolation. They don't touch the high voltage electricity at all. The shunt, however, is sitting right in the fire. It requires an external isolation barrier and a flawless amplifier. Third is power loss. The shunt is our heavy hitter here, but in a bad way because it uses the I squared R principle. It has the highest power loss and generates the most heat. The flux gate is moderate and the closed loop Hall is low. But the winner here is TMR. It is ultra low power. Fourth is the bandwidth. If you are using those fast silicon carbide inverters, we need a sensor that can keep up. The shunt and Hall are fast, but the TMR is the fastest. We are talking ultra high bandwidth up to 10 MHz. That is fast enough to see the electrical spikes that other sensors would totally miss. And finally, the mechanical size. The shunt is usually a large piece of metal on a bus bar. The Hall and flux gate need big magnetic cores, so they are physically bulky and heavy. The TMR wins here again. It is compact. It fits into a tiny chip package, saving us maximum amount of space in our junction box. Shunt is still the winner of most of the EVs today. They are cheap, reliable and safe. Closed loop Hall and flux gate are used when we can't afford the heat of a shunt or when we need plug and play for isolation. And TMR is the rising star. It is the future for 800 volts or 1000 volt systems where size and efficiency are everything. Well, that's all about the current sensing technology used in HV circuits. If you found this video useful, give it a thumbs up, hit the subscribe button and stay tuned for more exciting content.